Hello, my friends, and welcome back. Here in GSC 109 and the accompanying lab 109L, also known as Online General Physical Science 1. So this week, we are continuing our investigations and being able to take principles found in the world of physical science, physics, to be able to tell the story of the ebbs and flows of energy that are occurring all around us as part of our thematic section number 2. So before I begin with the rest of this week's weekly welcome, I want to be able to have a thought experiment, if you will. I have a question for you, the audience. What does, let's say, our wonderful blue planet Earth, have in common when we take a look at, say, the continents, the deep ocean basins, but also when we cut it through the middle? What does the interior of our Earth have in common with, let's say, a beaker that is full of water, a type of fluid, but also bubbling? And what do those two phenomena have in common? With a candle burning, these three objects help tell a story for this week. And that story is the much broader phenomena of heat transference, or the transferring of thermal energy. Thermal energy is an unseen but powerful force that drives much of the phenomena of the physical world. And we can tell that story this week. It's the energy that comes from the movement of molecules, in this case, particles, that manifest as heat. Whether you're feeling the warmth of sunlight, like out here on the coastline, or heating a meal in the microwave, or even observing the hot glow of lava, you are witnessing the transfer of thermal energy. But as physical scientists and students, we want to be able to ask ourselves the big questions. And one of the big questions that comes to mind that relates to the phenomena this week is, how exactly does this energy move around? And how can we harness it for practical use? What can we truly learn about this phenomena and tell it as a story? Well, the answer lies in the three primary mechanisms of heat transfer that we're going to cover this week. There's conduction, convection, and radiation. But within those ideas, there are principles that link all the way back into our earlier work in thermodynamics, but also branches out into heat, latent heat, phase changes, and the capacity that objects have to retain heat. So let's actually talk a little bit about those more in depth. Well, thermal energy occurs in three different ways. Conduction is the process in which heat is transferred through direct contact between molecules. For example, when we hit a metal rod at one end, the heat is going to actually transfer from one end to the next. And that's because the atoms that make up that metal rod are actually vibrating and moving and producing heat. And this heat transfer is particularly common in solids, where particles are closely packed together. Convection involves the movement of fluids, both liquids and gases, to transfer heat energy around. When the fluid is heated, it becomes less dense and rises while cooler fluids actually will sink. This circulation pattern can be observed in the natural world around us, and it creates ocean currents, weather patterns, and even
circulation of our planet's interior. And finally, we have radiation. In radiation, a heat transfer is being transmitted through electrical magnetic waves, such as the warmth you feel from the sun. Unlike conduction and convection, radiation doesn't require matter to transfer. We're all experiencing it, and it can occur even in the vacuum of space, making it relevant for later parts of the course where we start to learn things about how we can learn about the radiation being emitted from stars based upon their temperature and their color. And in order to be able to experience that, we need to be able to observe that radiation. And this is why sunlight also heats the earth, but it's still traveling through that emptiness of space. Matter changes from one state to another. We call it a phase change, like ice melting into water or water evaporating into steam. Thermal energy is still involved. And we need to be able to take a look at the concept of what we call latent heat. And that is the energy absorbed or released during these phase changes that allow for the natural flux to occur. And when we take a look at latent heat, for instance, when ice melts, it's absorbing heat, but its temperature is still remaining consistent at 0 degrees Celsius until it has completely transformed into water. Water will remain at 100 degrees Celsius when it turns into steam. And I think that's a really interesting phenomena because understanding latent heat is crucial for grasping the complexities of heat transfer during the phase change transitions, and has applications in, say, better understanding weather systems, like the formation of clouds and the severe weather. Heat capacity refers to the amount of a substance can absorb before its temperature begins to rise. Again, let's go back to the example in water, where it has a high heat capacity, meaning that it can take large amounts of energy, thermal energy, without significant temperature changes. This property plays a major role in regulating our climates, as our oceans, large bodies of water, absorb and store and then redistribute vast amounts of heat that comes in from that solar radiation. And it keeps the Earth's temperatures stable unless human impacts are involved. Isn't just energy that transfers from one object to another, but it can also be harnessed for work. And that's what we're going to learn about also in this week's module, because we want to be able to use it to create usable energy. This is the foundation of heat engines. Think of your steam engines from the previous week and modern power plants, like the one found in Mount Storm, West Virginia. In a steam engine, for an example, water is heated to create steam, but it's expanding and pushing a piston and converting thermal energy into mechanical work. Similarly, power plants burn fuel to produce heat, which is then used to generate turbines using the same steam that's also was generated in that steam engine example. And it's converting thermal energy into electricity, which I think is a really great phenomena for us to study as physical scientists, because it aligns with the first law of thermodynamics, which states energy cannot be created or destroyed, only transformed from one source into another. And by turning thermal energy into mechanical work, we are abiding by that first law and producing electricity and using it for practical ways. However, not all the heat can be converted into useful energy. It does escape. And that's where the second law of thermodynamics comes into play. Some energy will always be lost during the transfer process. It's part of that equilibrium or flux that I bring up quite a few times in this class. Often, waste heat energy dissipates naturally into the environment. And this is why thermal energy is inefficient, but not all thermal energy can be converted into work. And so that's why thinking about how we can take a heat source and then use that heat source to advantage by producing work using our technology is a great way to think about how we need to think about heat transfer because it's transferring from our thermal energy into electrical energy, which we'll talk about later in this class. I don't know about you, but one of the key concepts or themes that I want you to walk away from in this course is also having a appreciation of scientific literacy and awareness. In our labs and our reflections, we're all about learning about and improving our scientific literacy, but what about our awareness? There are key scientists that helped contribute to better understanding heat transfer as it relates to the evolution of what we define as thermodynamics. And that's why I use the heat transfer module after thermodynamics. So that way you have a nice conceptual approach to be able to address both heat-based phenomena. And when we take a look at the key scientists, our understanding of thermal energy transfer actually evolved through centuries of work, scientific breakthroughs. Some of the ones that I like to remember is Sir Benjamin Thomson and Count Rumford in 1798. They were the first to challenge the idea that heat was a fluid, and they demonstrate that heat is actually being generated through motion and friction, which synergizes with the idea that we're looking at the particles and the molecules, the microscopic components of this phenomena. Later, James Prescott Joule, sounds familiar, in 1840 made critical discoveries about the relationship between heat and mechanical work that I just talked about. And he shows that energy can be converted between different forms, and that laid the foundational groundwork for those laws of thermodynamics, especially that first law. And then building upon Joule's work, we still have who we already learned about, Rudolf Clausius, who developed the second law of thermodynamics in 1850. And he explains that heat naturally flows from hotter objects into cooler ones, and external work is applied. And it governs everything from the operation of our heat-based steam engines, as seen in trains, which shaped our Appalachian region, to the understanding of entropy, a measure of disorder in energy systems that is closely relied on by physical scientists to help explain phenomena, because we are all about understanding that the world around us is in flux. It's always changing. And when we look at the physical science phenomena, we can explain that change.